We're now going to do some examples of optimization problems. And so we're going to start with this simple one here. It wants us to find the dimensions of a rectangle that maximizes its area, given that its perimeter must be 50 inches. Okay, so if I draw a picture, this is always a good place to start. So we have a rectangle, right? And we have the length of the rectangle, or the length would be here. This would be the width of the rectangle. And the area of the rectangle is just the length times the width. And we want to maximize the area. Now, without any constraints, we could just make the area bigger and bigger just by increasing the length or the width or both of them. Okay, so you wouldn't necessarily be able to maximize that, but we have a constraint here, and it tells us that the perimeter of the rectangle has to equal 50 inches. So the perimeter is just 2 times the length plus 2 times the width. And this perimeter is going to form a constraint on L and W because they have to be 50 inches. So I would have like 2L plus 2W is equal to 50. And now what we're going to be able to do is use this constraint to get this formula for the area all in terms of one variable. And that's what you want. You want a function for the... What I want to maximize here is the area of this rectangle, and I want a function of the area all in terms of one variable. And so I can use this constraint. So what I'm going to do is I'm going to solve this constraint here for L. So I'll get like 2L is equal to 50 minus 2W, and then I can divide both sides by 2, and then I get L is equal to 25 minus W. Okay, so what I can do here is place this into this formula so that my area here is all in terms of one variable. So in for L, I'm going to put 25 minus W. And then we have the W there. So this is L times W. It's just L, according to this constraint, has to be 25 minus W. And so now what I have here is a function of A here, which would be 25W minus W squared. And we know that this is an upside down parabola, and so this would give us the area for different values of W. And so of course an upside down parabola has a maximum value, right? And that would be the maximum area, and you would find the W for that. So let's just go ahead and use calculus instead of finding, because this thing would be like this. It would start at 0, go up. It'd be like that. And so the opposite of B over 2A would give us the vertex, and this over here would be like the maximum area. This would be the W, right? Because this is a parabola. Okay, W is the opposite of B over 2A. So we could do that here, where in fact this would be the opposite, W squared plus 25W. So the B would be 25, and then A would be -1 in this case. But what I'm going to do is I'm going to go ahead and I'm going to use calculus. We're going to maximize this by taking the derivative here and setting the derivative equal to 0. But also let me define an interval here. Okay, so my interval, technically I wouldn't get a square if either of these was equal to 0. Okay, so my W here, we're going to say it can't equal 0, because if W equals 0, this area would equal 0. Okay, but it could be anywhere up to 25. Now, if W couldn't equal 25, because then L would equal 0. So I'm going to leave that out too. And so we'll say anywhere between 0 and 25. And if it were really close to 25, it would be a long, skinny rectangle, right? Very, very skinny. Okay, but it can be somewhere in between there. So we have an open interval, not a closed interval, but really the endpoints here if I check these endpoints, I would get 0 in either case, and that certainly wouldn't be the maximum area. So there better be a relative max here for this function, and there is, because we know that this is a parabola that's upside down. But let's go ahead and take the derivative, dA with respect to w, and when I do, I get a negative 25w plus 25. And then I'm going to set my derivative equal to 0, and then we're going to solve and find the critical point. So negative 2w is equal to negative 25. Divide both sides by negative 2, and my w is equal to 25 halves, okay, which is like 12 and a half. And 12 and a half inches. And notice that this is actually going to be the same that you would get through the opposite of b over 2a, giving you the vertex of the parabola. So the calculus is going to give you the same thing. But we never did check. Normally, you would want to check that this is indeed a relative max, because a critical point doesn't have to, it could be a min or it could be neither. So the easiest way in a lot of these problems to check is going to be to take the second derivative and use the second derivative test. So I'm going to take the second derivative here with respect to w, and it would look like this. And the second derivative here is just going to be negative 2. And it's going to be a constant. And so my second derivative here is definitely negative. Doesn't even matter what w is. It's always negative, which means it's always concave down. Which the parabola is always concave down, right? And so w equals 12.5 is a relative max. That is the w that would give you the maximum area, okay? And so notice then that L would just be 25 minus the w, 12.5, which is 12.5. And so what that means is the dimensions of this perimeter that's going to maximize the dimensions of the perimeter, or the dimensions of this rectangle that's going to maximize the area is 12.5 by 12.5. So it'll be a square. The square is actually what ends up maximizing the area, and it's not going to matter what this perimeter is. You end up maximizing the area with a square, as it turns out. Okay, well now I'm going to do something similar. Let's take a similar situation, except now I'm going to kind of flip it around. We want to find the dimensions of a rectangle that minimizes the perimeter, given that its area must be 100 square inches. Okay, so we want to minimize the perimeter now, not the area. And of course, we could minimize a perimeter just by shrinking our rectangle down and bringing L and W, making them smaller and smaller and smaller, except our rectangle has to be 100 square inches. So the area has to be at least 100 square inches, and so that forms a constraint, right? So the formula that I want to maximize is the perimeter, which is like 2L plus 2W. And I should say optimize. I don't want to maximize this. I want to find the minimum value, and finding a minimum or maximum is optimizing the function. So I want to optimize the perimeter, and in this case find the minimum value for the perimeter. So this is the length, this is the width. And now my constraint is the area. So the area is just the length times the width, and my area has to be at least 100. So L times W has to be 100. And so we're going to use this constraint to put all of this in terms of one variable. Okay, so and let's put it all in terms of W, I guess. So L is equal to 100 divided by W. And then I can place this into this equation up here. And then I get that the perimeter is equal to 2 times 100 over W plus 2W. Okay, and then I guess I could simplify this. It would be 200W plus 2W. And now I want to find the minimum value of this. Now the whole thing about the parabola and all that doesn't come into play here, because this certainly isn't a parabola. It is some other function that we know little about. So I'm going to take the derivative here, and we're going to find the critical point. Oh, and we should also notice that this is also going to be between 0 and 25. And technically, it couldn't be 0 because it wouldn't be it wouldn't be an actual square, and it wouldn't have an area of 100. Well, it couldn't be 0. W couldn't be 0 because the length here would be undefined, right? And let's see. W here. Oh, we want to minimize the perimeter. Well, W could be 25. Is that right? We'd have well, that's a good question. I suppose if W were 25, the length would be 4, and then the area would be 100, and so yeah. So I mean, you could include 25. So I think what this would need to be is it can't include 0, but then technically I think it can go up to infinity. It's just the length would keep getting smaller and smaller. So really, again, we don't have a closed interval, and so we want to find any critical points, and hopefully the critical point is a relative minimum. And so let's go ahead and do that. So this is going to be negative. It's like a -1 exponent. I'm bringing that down. -200, subtracting 1 from the exponent will give you a -2 exponent, which would be W squared, like that. And then this is plus 2. So this is dP dW. Okay, so this is my derivative, and now I'm going to set my derivative equal to 0. Okay, and now I can move that to the other side, and if I do, I get 2 is equal to 200 W squared. Now I can move the W up here and the 2 down there, so I get W squared is equal to, if I do that, 200 divided by 2 is 100. And so my W is going to be the square root of 100, and only the positive square root makes sense here, because you can't have a negative with. So I get 10. But I need to know if this is really a relative min, because who knows? It's a critical point, but it could be a relative max, or it could be neither. So what I need to do is perform either the first derivative test or the second derivative test. And again, the second derivative test, if it works, is always the easiest. Well, almost always the easiest. So what I'm going to do is take the second derivative. In this case, it certainly is going to be the easiest. So I get d squared p over dw squared. That's the notation for the second derivative. And then I'm going to bring down a negative. So this is like, you could think of this as -200 w to the -2 plus 2. So this is like bringing down that -2. So it's -400 w to the -3. And then the 2 just goes away. Okay, so then I could rewrite this as -400 over w cubed. So notice if I put a 10 into here, doesn't matter what the actual value is. I know it's going to be negative because this will be positive, and we have a -400 on top. So this will be less than 0. And what that means here is less than 0 means that it's concave down. That's a problem. Oh, I know what the problem is. When I bring down the -200, that gets rid of this. So there is no, sorry about that. And so just erase this, and let's just show that d squared p over dw squared evaluated at w equals 10 is actually going to be greater than 0, which means this thing is concave up, and you get a relative min. So in other words, this is going to be a relative min of the function, and that's actually the only critical point other than 0 here, and 0 isn't defined in this situation. So this is really the only critical point, and you do get a relative min, and so this will be the dimensions that minimize the perimeter of the rectangle, and the rectangle will still have a area of 100. So the length here, the length is going to be 100 divided by 10, which is 10. So you really have 10 inches by 10 inches. So this is going to be the dimensions of the rectangle that has an area of 100, 10 by 10. And so it has the area of 100, but that's going to minimize the perimeter, which in this case would be 40. And that will be the dimensions that give you the minimum perimeter. Again, it's a square, right? So it looks like when things are square, it optimizes things, doesn't it? When you're dealing with a rectangle anyway. It seems like it gives you the maximum area, minimum perimeter. So that's interesting. So now let's do a slightly different situation where it won't necessarily be a square. And so this situation is we're going to build a fence here, and I have 120 feet of fence, and I'm going to use it here by building a pen, a kennel or a pen up against the barn. So the barn wall forms one side, and so really the fence just needs to give me these three sides, L, or we'll say that's W, W, L, and W, right? And so this constraint of 120 feet of fence here, 2W plus L has to equal 120 feet. Okay, so what this is saying is I have fence that's going to make up these three sides of this kennel, and I have 120 feet of that fence, so 2 of these W's plus 1 of the L's has to equal 120. But I want to maximize the area of my kennel, and the area is the length times the width. So I'm going to do what I did before, but now my L here, I'm going to get this all in terms of W. I'm going to move the 2W to the other side, and I get L is equal to 120 minus 2W. Okay, so now my L is equal to this, so my area is going to be 120 minus 2W times W. So what I want to do is I want to maximize this area. So this is 120W minus 2W squared. Again, this is a upside down parabola. It would have a maximum, but we're going to go ahead and use the calculus here. So we're going to maximize that. I'm going to find the derivative, and I'm going to get 120 minus 4W. Okay, I'm going to set that equal to 0. 120 minus 4W is equal to 0. So I get 120 is equal to 4W. So my W, divide 120 by 4, and you get 30. So it looks like my looks like I get 30 feet for my width, but I better make sure that's a relative max. And so what I'm going to do is I'm going to take the second derivative, and I'm going to get negative 4W. And then if I put in 30 here, this is going to be less than 0, which means it's concave down, which means W equals 30 feet is a relative max. Okay, and so that's going to be what maximizes the area. So now I can put in 30 feet here, and then I'm going to get 60 feet for my length. So what are the dimensions? It's going to be 30 feet by 60 feet. So if I have 120 feet of fence and I'm going to build a kennel using the side of the barn as one of the lengths, then this is going to be the dimensions that maximize the area of the kennel. And so that's a nice application problem of this. So, okay, in the next several videos we're going to do some more examples of optimization.